So today I'm going to talk to you about MAST, and in particular, a little bit of behind the scenes look at how we manage things at MAST, and in particular, how we empower some of the surveys, some of the queries that users perform. So a quick overview for those not familiar with it. MAST is a Mikulski archive for space telescopes. That's what the initial stands for, and it is basically our a conglomeration basically of a lot of data across lots of different missions. Today in particular, I'll be focusing on our multi-mission observational database. This contains over 60 million observations across more than a dozen missions. You're seeing here a little animation I've created, which shows you the sort of exposure time coverage of 3 missions, just 3. HST Galax, which is what's showing up now in sort of being highlighted here, and TESS, which will start up in 2018. So this little movie goes from 1990 to 2021. The HST data is a little bit hard to see just because the field of view is so small. Galax is very prominent because it's a survey mission, and TESS, when it shows up, because it covers so much area, will be quite prominent. I'll be providing a link. This link is now public, and we'll be providing that later on today. This is the TESS mission now, covering pretty much the entire sky. Why didn't I put more missions? Because everything would be covered up pretty much. We have a lot of data as well. Oh, and I should mention that we have a sonified version. So there's no audio here, but the sonified version just has a different note for each week as the data goes in. So you can actually hear the differences when HST or Galax or TESS is being loaded beyond just visually. So as I mentioned, MAST contains a ton of data, a lot of different observations. This pie chart is just showing you the number of observations, so not the actual sort of file sizes, not catalogs or anything like that. This is just what is in the multi-mission database in terms of number of observations. You can see that we have a lot, especially from HLSPs, high-level science products. So this is community contributed data. And this is one of the strengths of MAST, right? So the community can contribute to us and provide data that then becomes accessible in the same way that you would access HST or TESS, or in the future JWST or Roman, Pan-STARRS, that's PS1, and things of that nature. And we have several different ways to access the MAST data, the MAST portal, Astroquery.mast, table access protocols, and a handful of others. So that's what MAST is. Let's go over sort of a brief sort of workflow of like how you would access MAST data before I dive into how how we make this happen. So let's start with the MAST portal. I'm not going to go over a full tutorial for this. I will point out that in our YouTube channel, we have several recordings from Chinwe Ideani that sort of go over all of the details of using the portal. But at its very basic, you can put your target name or your coordinates. You can click search, or you can also do an advanced search if you want to filter out a little bit more, have a little bit more control over your results. You get a grid of results. I have filtered them here by saying, just show me HST data, and I can see it here. There's also a viewer that shows you the footprints of the particular observations. These are all observations. When I'm interested in one, I can either click the ... or click the checkbox and click this to add to basket. So basically, I am selecting a single observation and I'm saying, I want to learn more about this observation, right? I've discovered in this 863 total rows, I filtered it down to 56 HST observation. I'm clicking one and I'm saying, I want to know more about J96U01010. That gets me to the download manager, sometimes also called the download basket. This is where I am sort of getting more details of the particular observation I was interested in. I can see all of the files for that observation, and I can also see members of that observation. So in this case, this is an HST association. An association for HST is built out of the individual members, which you can see here. So I can access those members and I can access the files from them. I can also see related observations. These ones at the top are HAP. This is the Hubble Advanced Products, which are built from some of the same files. And so all of this data is sort of related together and is accessed when you go to the download manager. So the basic workflow, you search for observations via some criteria, whether it's location on the sky or any other filtering, and then you click to gather files for those observations and also identify related observations. If you were using Astroquery.mast, the workflow is very similar, except you would be typing it out in Python. For example, you would do from Astroquery.mast import observations. You query your favorite object, which happens to be the 4046 Sagittarius. You get 862 rows, just like before. If you filter by HST, you get 56, just as before. If you select your target, your observation that you want to learn more about, you can pass it along to get product list. I pass that observation along, and I get 42 possible files, and I get descriptions for each one. So that's a basic workflow, whether you're using the portal or Astroquery.mast. How do we make this happen, right? How do we get all of these observations? How do we get all of these files? Well, the metadata in the MAST multi-mission database is stored with something called the Common Archive Observation Model, CAOM. Is one of my favorite things about it. It's a data model that sort of generalizes the metadata information for any mission, project, telescope that we put into this database. So everything in the database conforms to this model, whether it's a contributed data set from HLSP, whether it's ground-based data from PanSTARRS, whether it's space-based data from HST, whether these are planned observations for JWST, right? So everything conforms to this model, which means if you understand this model, you have a lot of power in terms of identifying these data sets. This model is used in other archives and it's been developed with them as well. So for example, ESAC and C80C, it's being considered as well for Spitzer and Rubin. So you will probably see more CAOM being used throughout the astronomical community, with the caveat that obviously we try to make this as transparent or to users as possible, right? We don't put CAOM right in your face and you have to learn this, right? We create user interfaces that rely on it to give you a simplified view for the public. So this is how CAOM looks like. There's actually 3 levels to this, but I've cut it out because there's only the first 3 are sort of used at Space Telescope with any regularity. At the top level for this data model is the observation itself. The observation refers to the acquisition of the data, what telescope, instrument, proposal, etc., etc. So this is basically the key information for an observation. An observation can have members, any number of them. So this 0 to star is basically there can be no members, or it can have any arbitrary number of members. So basically an observation can refer to another observation, which can refer to another observation. So that's how we can link them together. Each individual observation, regardless of whether it has members or not, can have any number of planes. Again, from 0 to an arbitrary number. The plane, this is a bit of an arbitrary term, but the plane refers to processing metadata and coverage metadata. So we're talking where in space, right? The footprint, when in time, the time, the temporal coverage, and the energy. So what filter, what bandpass has been used? Is this optical, ultraviolet, that sort of information? And the processing, the calibration level of the files associated with that particular plane, with that particular observation. The calibration levels, I just list them here for sort of for reference. These are the CAOM calibration levels. You'll see why I specify that in the next few slides, but it goes from -1, which are planned observations. Right now we have JWST planned observations, for example, for cycle 1, all the way up to 4, which is contributed data sets, that is high-level science products. For each plane, there can be any number of artifacts. An artifact is, again, one of these arbitrary terms, but it represents the file metadata. So what is the file name? What is the checksums for the files? The URI is stands for Uniform Resource Identifier. It's basically something of this form. The archive, the mission, some arbitrary things. In this case, it's product. Sometimes it can be exposure. Sometimes it can be a preview, and the and the file name itself. This is used for abstracting out the location of the file, so we don't store, the path on disk. And our services do use the URI as input. So, for example, you can call the MAST API, you can pass this URI, and that will trigger a download for this exact file. You do not have to know where the file is, and this is also powerful because if there are HST files, for example, in the cloud, in AWS, you can pass the same URI and access the data in the cloud as if you were on disk, or right, or on premises, right? So it's this abstracts away the need to specify different locations for things on disk versus things on the cloud. So in general, these first two things, observations and planes, they allow you to do data discovery, right? With the instruments and the location on the sky, you can find observations. Once you want to access the data, you would use the artifact information to get basically file locations, file names, and things of that nature. So data discovery and data access. That's how I would split these apart. So let's go back to our workflow and describe a little bit more in detail. So this is step one, data discovery, right? So you're typing out your observation, or sorry, you're typing out the target you want to look for, either in the portal or in the Astroquery or in or through our MAST API, and you get your results back. What's happening here is that we are providing you what's called a view. It's a combination of actual database tables. So a view is called ops pointing, and it is joining observations, it is joining planes, and it is also relying a little bit on the member table. This is showing you just observations, and that is one of the key things I want to sort of emphasize here. We're not showing files, right? So these are not files. These are observations. Observations contain files, but this data discovery step is just focused on observations. So that's sometimes one of the stumbling blocks when people first use the portal. They want to search for files. That's not quite how what's being returned here. So just sort of bear that in mind. Also, an interesting subtlety is that we want to provide the highest calibrated data available for you. We want to provide you basically the best science data possible immediately. So we hide through the use of the member table and this view, lower level members or calibrations. So you can see an HST association like this one, but in the list of results, you will not see the members of that association until you go to the next step and you go to the data access step. This is a decision we took because we want to keep our interfaces clean. We want to show you basically, again, the highest level of data available, because for the average user, this is what they want, right? They want the best processed data available. Obviously, if you want to reduce it from scratch, you can. You would just need to download the member data for it. A subtlety, again, about the calibration levels. What right now it's not being displayed here, but if you were to scroll down here, you would see filters available for the calibration level. I want to specify a couple of things. One is that this is the CAOM calibration level. So if you have been following some of the JWST webinars out there, you probably are familiar that JWST has multiple level 2, which is calibrated data sets, to A, to B, to C. All of these are CAOM level 2. There is no distinction between 2A, 2B, 2C in CAOM. Similarly, once we get more along with Roman, you may encounter things like Roman level 5. That is exactly the same thing as CAOM level 4. So this is a decision we've made because we want to make sure that when you search for calibrated data, you find calibrated data regardless of what the mission specific terminology is for that. So the power of CAOM is abstracting away mission specifics to give you the generalized picture. But it does mean that if you want something very specific for a mission, you may have to run through some extra steps to get exactly what you need. Another sort of subtlety is in the same way that we hide lower level members, we are hiding lower level calibration. So if you were to do an advanced search and say, give me every level 1 observation, what you're actually specifying is you want data that has reached only level 1 and no higher. Again, you can find it because you can always go to the access, to the data access step. The last region, the last sort of thing to point out here is, these footprints are created via a column called sRegion. So you can recreate this in Astroquery, in Python, basically, if you want, just because the footprints are one of the columns effectively. The data access step is the following. When you go to your download manager or the equivalent in Astroquery, this then takes some of the information that you had before from the ops pointing, which is COM, observation, and plane, and adds to it artifact members and this other table that's not part of the COM model, but we have anyways, called mass product descriptions. This mass product descriptions is basically the description you see here, the sort of human readable, oh, this is a DATS FLT file, that sort of thing, or this is a preview file, that human readable description, just to give you more information on the files. So this sort of access here gets you some of the related observations, right? It gets you the members and it gets you the associated data sets by querying CAOM members and a couple of other sort of similar tables out there. There is always a flag here for minimum recommended products. By default, this is clicked on for most users. What that means is that if you were to go back, for example, if you were to click just the save button, you would get the minimum recommended products. You would not go to the download basket. You would just immediately download the MRPs for that observation itself. So for J906, there's 2 of them. It's the science files for this observation. It's important to remember, or a subtlety of the MRP is that this is just for the top level observation that you have selected. Members, even if they have some of the same types of files, are not considered MRP, nor the associated data products, associated observations. So MRP just applies to the observation, the single observation you selected, or if you selected more than one in the prior step. And as mentioned before, the file locations are abstracted via the URI. You can see the URI here, for example. So in the interest of time, here's sort of a bit of a summary, right? So the MAST portal, Astroquery.mast, and use the CAOM metadata model. It generalizes the specific mission-based information in order to power searches across all missions at the same time. If you need more power beyond that, you can always use our Table Access Protocol Service, TAP. This is a virtual observatory standard, and it allows you direct access to the CAOM tables itself, which means that you can, for example, perform queries on file types instead of on observations. I don't have time to go over how to do that here, but again, I will always be, at the booth. We can guide you through some of that, and you can always reach out to us. I do want to give a plug for Scott Fleming's webinar tomorrow, I believe, on the new and improved HST forms. So we have forms in MAST that do not use CAOM. CAOM is used for multi-mission data, right? So this is our portal into anything that combines more than one mission. But we do have specific mission forms like the HST form. So an HST form like this one, as you'll see tomorrow, this is sometimes called MAST Classic in our terminology. This is another way to search for data with the caveat that it is only HST data, but it provides you a little bit more control over HST specific terminology. So 2 ways to search. Do you search via all missions through the CAOM powered multi-mission database, or do you search for a specific mission using one of our specific mission forms? With that, I will thank you for attending. As I mentioned, you can always reach out to us at the booth. It's hashtag EXP STScI. Always email us at archive at stsci.edu or at Twitter at Mast News. So with that, I will be happy to take any questions you may have.